we're going to talk about describing motion, and the first way we're going to talk about it is in graphing format. So we're going to start talking about the graphs and basic motion. So to begin, consider a car moving with a constant rightward velocity of 10 meters per second. So we have our little car here, and after 1 second it's gone 10 meters, and after 2 seconds it's gone 20 meters, after 3 seconds it's gone 30, and 4 seconds it's gone 40, so on and so forth. So what do you think a position versus time graph of this motion might look like? The thing to really think about is positions on your y-axis, time is always on your x-axis, and this is going pretty constant. As the position goes up, the time goes up, or as the time goes up, the position goes up. So this is a direct correlation. So our position versus time graph would be a linear line that looks like this. Now notice that we have our position labeled on our y-axis with its units. We have our time labeled on our x-axis with its units. We have a good scale on both axes. They don't have to be the same. And then we plotted points. There's a point at each one of these spots. And then we did what was called a best fit line. This one actually goes in a straight line. And that's because it's going a constant velocity. Now let's consider, though, a car that's moving with a changing rightward velocity. Okay, it's a positive velocity because it's going forward, but now it's changing. After 1 second, it's gone 2 meters. Oh, that's the end of the school day, but we're going to keep talking. Okay, so after 2 seconds, it's 8 meters. 3 seconds, it's 18 meters. So this one might not be so direct like it was earlier. So its graph shape is going to be a little bit different, but we still want to look at a position versus time graph. Notice this graph, though, is more of a curve. And so as we change, that best fit line can be more of a curve if you can get more of the data points on it. But a best fit line or a best fit curve should always be what you do. Now, this is important for several reasons. The reason this is really important is the slope on a position versus time graph tells you the velocity. If you remember in math, they've taught you that slope equals the change in y over the change in x, which also is y2 minus y1 over x2 minus x1. Another way that most of you remember it is rise over run. But again, the slope of a position versus time graph is velocity. All right. So, and the slope is of this particular graph. Remember we did 10 minus 0 over 1 minus 0, which would just give us 10. We can do this from any set of points. So I could have done 50 minus 20, which would have given me 30, and then I could have done 5 minus 2, which had given me 3, and so that would have given me 30 divided by 3, which is 10 meters per second. So everywhere along this line, the slope is 10 meters per second. So we're going to do this actually in class together, all right? So we are going to, well, we'll go ahead and do it now. So I have a distance versus time graph here, which could also be said a position versus time graph. I really do like the words position and displacement better because it tells us directional information as well. So I have the change in x, which is my position, divided by the change in t, which is my time. So I have the numbers 4 minus 0, and then I have 8 minus 0. So that would be from point A to the origin. And so that would tell me it's 0.5 meters per second. Well, if I look, since it's on a straight line, B is actually going to be the exact same thing because it would be 8 minus 0 and 16 minus 0, which would give me 0.5. So whenever you have a linear line like this, then the velocity is constant. So it's the same for A and B. So if we ask what's the car's average speed, well, average speed is total distance divided by total time. So the total distance here that I show on my graph is 10, and the total time is 20. So 10 divided by 20 is 0.5. So it is the same the whole time. But it is key that you remember that average speed is total distance divided by total time. That's what average speed is and how you find it. Okay. Now, what is its acceleration? Hmm. I just said that at all these points it was going 0.5 meters per second. That's like me saying my car at every single point going from in front of Valero to in front of Berkshire Brothers to in front of Kroger is 35 miles per hour because, I don't want to get a ticket. So if that's the case, my car's on cruise control. Am I accelerating? No, not if my car's on cruise control. So the acceleration here would be 0 because acceleration is the change in speed over time. So I didn't change any speed, so I'm not accelerating. And so that's 0 meters per second squared. All right. So we're going to compare these motions and we can think about it as a trip. So I want to compare the red line. So the red line is going pretty constant speed. So it's like set it on cruise control and just going. The green line has less of a slope. So that must mean it's going a little bit slower. Okay. It's still taking 20 seconds, but it's not going as far in 20 seconds. So it's going slower. Again, it's telling the slope is telling me it's velocity. Lower velocity, lower slope. So now with the blue line, that person went 10 meters in 7 seconds. So they went a lot faster. So that's saying that the velocity is higher. Higher slope, higher velocity. Now the orange line just says that they went 7 meters and they started at 7 meters and they stayed at 7 meters. That means that they were just sitting still. So that person doesn't have a speed. The slope of that line is actually 0. Now the black line, it looks a lot like the red line, but it's just the opposite direction. And that's because it's coming from wherever we were and coming back to where we started. So really, this is the same slope, but it's negative. So that means that it's still going 0.5 meters per second, but it's now going in the opposite direction. So this would be like, let's say this was just going from Kroger to um, Starbucks on the lake, okay? And we didn't hit any lights and we were on cruise control. Well, this would be us coming from Starbucks back to Kroger on cruise control. Okay, now this one, this one's my one like I'm sitting um, at, so if I said 0 was the high school, then I'm sitting like at Valero maybe. Um, and then I'm going to Waterburger because I want to get me, some French fries. And then I sit at Waterburger and then I turn around and I come back to the high school. That would be what's going on here. And I could find my speeds at each one of these trips. Whereas the person that's the red line, they're just going from the high school and then they're going to like Walmart because they're going a little further than Waterburger. Okay? Interesting little pieces of information we can get from our position versus time graph. So what if the shape of the graph is a curve again? That means that the object is now accelerating or changing velocities. Now, to find the slope, okay, I think I was hitting the wrong buttons. To find a slope of a curve is kind of difficult. So, There's lots of different ways that we can do that, but really you just take a point and you can take two different points along the curve and you can, so we could say 3 and 18, and then we could say 3.5 and 23, and we could find a slope. And then we could go to a different spot and we could take a different set of data points. And we could say, 1.4 and 6 meters and 2 and 9 meters, and we could find that. So then we could do those two velocities and divide it by the amount of time difference we had between them. So there's a lot of different ways to do it. But it is changing velocities. It's not the same the whole time. It's accelerating. So the instantaneous velocity, this is a vocabulary word for you, of an object at a certain time in the slope is the slope of a position or displacement versus time graph. It can be positive, it can be negative, and it can be zero. If it's positive, we're going forward. If it's negative, we're coming back or towards. So we switch directions. And then if it's zero, we're sitting still. So remember, those instantaneous velocities can be determined on the slope of a position versus time graph. So we can find the instantaneous of that one single object right there. Even though this has a curve, we could say, at this one single second, what were we doing? And we could figure that out. Okay? But the slope will give us the velocity. That's the key thing to remember. So there's one thing to remember. Slope equals velocity for a position versus time graph. What in your car shows you the instantaneous speed? Think about that. Hopefully you said your speedometer, because that's what shows you the instantaneous speed. See you in class.